So we just looked at the SN2, right? Now we're gonna look at the SN1. So I'm going to give you just a generic overview of what happens during the reaction. You already know that this, is it concerted or does it go through stepwise? Okay. So, but we're going to start off with an alkyl halide. Right? We're going to react it with a nucleophile.
With an alkyl halide or an alkyl? Okay, yeah.
I'm just saying that a halogen is attached to it, right?
Okay,
so it's an alkyl halide. React it with a nucleophile. And we'll have the nucleophile substitute for whatever halogen that we had there. Right? So let's say we begin with something like this. Right? The first step of the reaction is going to be that the leaving group is going to leave. And once the leaving group leaves, we're going to generate our carbocation. Right? Once we generate our carbocation, the nucleophile can come in and attach at that center, and we'll generate our product. Cool. What's the rate determining step in this reaction?
The leaving group when it leaves.
That's
like
right.
It can.
So notice that there's two steps, right? This is the first step. This is the second step. So this first step is a rate determining step. This is the rate determining step. So and this step depends just on the leaving group leaving. That's why it's SN1, because the rate determining step is dependent just on one species, right? Okay. Now we're going to analyze this. Alright. So we're going to start off with the kind of substrate that we want to use. And in this one reaction, what kind of substrate do we want to use?
A really substituted one.
Okay. So we want tertiary over secondary over primary over methyl. Then which one did we say would not happen?
Methyl or primary.
Okay, so these ones will not happen. Okay. Now in this case, now we're going to be using still we're going to be using a nucleophile, just like in the SN2. But what kind of nucleophile are we using?
A strong nucleophile.
Not a strong nucleophile. We're going to be using mainly a poor nucleophile.
Right, SN1 is SN2.
Right.
Why?
Because the rate determining step is just determine. We just want the leaving group to leave, right?
So it doesn't matter what the nucleophile is?
Yeah, it doesn't really matter, but it's better if it's weak.
Okay.
Because the strong nucleophiles are going to be doing the SN2, right?
Mm.
Yeah, so we want a poor nucleophile for the most part. It doesn't really matter, but we're generally going to see SN1 when we have a poor nucleophile, right? And a poor nucleophile in most cases would be something that does not have a charge on it. So an example of this would be like H2O or some kind of alcohol, right? So these don't have any charges on there, all right? Poor nucleophiles are generally also poor bases. Generally. Okay. So we just looked at its substrate. Looking at SN1 reaction, we're seeing that the substrate that we want is a more substituted substrate. The nucleophile that we want is a poor nucleophile, right? You think about the solvent. What kind of solvent did the SN2 react in? What kind of solvent did the SN2 react in?
I don't remember.
So it was polar aprotic. It was a polar aprotic solution. Or
It's
solvent.
gonna be a polar protic.
That's right. This is going to favor polar protic.
So it can make hydrogen bonds.
That's right. Which means solution form hydrogen bonds so the reason why we're doing it in a polar protic solvent is because these hydrogen bonds that we're going to create are going to stabilize the carbocation. Cool. You okay with this? So the hydrogen bonds are going to help to stabilize this carbocation. This is why it's favorable.
Okay.
So what kind of solvent do you think E1 will be in?
Like H2O maybe.
Does E1 go through a carbocation?
Does what?
Does E1? We're kind of jumping a little bit. Remember, or maybe we haven't
We haven't talked about E1 and E2.
we probably haven't combined it yet. Okay. We haven't combined it yet. Okay. No worries. We'll get there. What's the last one? Stereochemistry. Alright, so the SN1 is gonna have a certain stereochemistry to it. So like you already know, it's gonna be going through a carbocation. The SN1 goes through a carbocation, and it turns out that the carbocation is flat or planar. So I'll just give you an example of this. So let's say you started off with this this molecule here, right? Start off with this molecule here. Now this molecule, now once the chlorine leaves, we're going to generate a carbocation here, right? Now this carbocation, this molecule now has become flat, right? So that means that the nucleophile that's going to come in, because the SN2 is just a substitution reaction, the nucleophile that comes in can come in from the top or the bottom.
You're still talking about SN2?
SN1.
Okay.
Right. So this is the nucleophile. Then once we form that carbocation, the nucleophile is going to come in and attach. So it turns out that because this carbocation is planar, meaning that it's flat, the nucleophile can come in from the top or the bottom.
Okay.
So what that means is that we're going to generate a racemic. Our product is going to be racemic.
What does racemic mean?
It just means that we have equal proportions of both enantiomers. So since we're flat, the nucleophile will come either from the top or the bottom. We're going to produce racemic product, meaning that we will generate both enantiomers. Cool. Alright, just a couple quick questions. What is the stereochemical consequence of an SN2 reaction?
What do you mean by consequence?
Like what does it cause? If I did an SN2 reaction, what would that do to the stereochemistry of the product that I would form?
I don't know.
Does anything happen to the structure if we do an SN2 reaction on it?
Doesn't it become like either inverse something
Inversion.
or inversion or something?
Yeah, so either inversion or we get either inversion or retention.
Okay.
Right. So do you know why that would be happening?
It depends on like where it comes in, like from the top or the bottom, right?
That has to do with the SN1.
Okay, no,
Right.
I don't know.
Okay, so we'll go back up what we had before. It's okay if you don't know, it's okay. Alright, so this is what we said about the SN2. in terms of substrates, we want the methyl primary, secondary, tertiary won't happen because there's too much steric hindrance on there. Because the SN2 reaction, the rate of the reaction is dependent on the substrate and the nucleophile. That's why we have two on there. Now, we don't want a lot of steric hindrance because the mechanism is that it's going to go through a conserved mechanism.
Right, so it wants
we don't
to go
wanna,
at the same time, yeah.
That's right, so we don't want a lot of crowding.
Right.
The nucleophile, we want a strong nucleophile for the reaction to occur because the nucleophile, the rate of the reaction is dependent on the nucleophile. Right? The rate of the reaction of SN1 is not dependent on the nucleophile.
Right.
It's dependent on the leaving group leaving.
Right.
Right? But this one, the rate of the reaction is dependent on the nucleophile and the substrate.
Yeah.
Now, the solvent we want, we want it to be in a polar aprotic solvent, like we said. Polar aprotic solvent, meaning that it's going to be polar, right? There's going to be an unequal distribution of electrons, and the solution should not be able to form hydrogen bonds. And we gave some examples, right? Acetone, DMF, DMSO, THF, right? Then in terms of stereochemistry, we said we're going to be doing a backside attack, right? Which means that the nucleophile here, this is our nucleophile, right? It's going to come in from the backside and kick out this chlorine, right? Which will lead. So the act of this guy coming into the back here and hitting this carbon here, right, is going to cause these three to shift this way, right? Yeah. That's that inversion of geometry or inversion of configuration. Okay. Right? That inversion of configuration, we said, could lead to an inversion of stereochemistry. Right? So we said that if the nucleophile coming in and the leaving group, if the nucleophile coming in and the leaving group, if they have the same priority, right, then we will indeed get an inversion of stereochemistry. Right. So what is the stereochemical consequence of an SN2 reaction?
Potentially an inversion.
Inversion of what?
Of stereochemistry.
Okay, kind of. So
or of configuration, you mean?
Okay, but we must get, so we must All right, so while we're waiting for it to come up. All right, so in terms of the stereochemical consequence of the SN2 reaction, we must get inversion of configuration. Right? And this inversion of stereochemistry can lead, right? So that means we can get inversion of stereochemistry. An inversion of stereochemistry just means if we started off with an R, we would get an S. So what is the stereochemical consequence of an SN1?
I don't know.
Alright. Okay, so what we were saying is that's one reaction. We're going through carbocation, therefore favoring tertiary, secondary substrates over primary methyl. And the reaction will not occur on a primary or a methyl. It will not occur on a primary or methyl. And in terms of nucleophiles, we're looking for poor nucleophiles, or we don't really, our nucleophiles don't need to be that strong, because the rate determining step does not depend on the nucleophile, only the substrate. And then we went into the solvent. We said we're going to be using polar protic solvent because the hydrogen bonds stabilizes the carbocation. Then we said in terms of stereochemistry, we know that we're going through a carbocation. The carbocation is flat. We know that once we form that carbocation, the nucleophile can come in from the top or the bottom. So that means we're going to produce a racemic solution, which just means that we generate both enantiomers. So the consequences that we produce.
Didn't we also talk about like hydride shifts and methyl shifts?
Okay.
I think we talked about it, so it's okay.
Okay. No, that's a good point. So we can add that on here. That's a very good point. Thanks for bringing that up. So we'll add it. So this can be more complete. And if you notice anything else, we can add it on here too. So now we know about carbocations. We know that they can rearrange. Right? So why are these carbocations rearranging?
To become more stable.
That's right. So we're going to rearrange them because we want to become more stable. Right. And there are three main kinds. First one is hydride shift. You know the second one?
Methyl shift.
And for the last one, we're gonna say, sorry.
So then, what's the last one?
It's a ring expansion.
Oh, right.
Right. And in the case of the ring expansion, all it is, we're trying to create a larger ring, preferably 5-member or 6-member ring, because we want to become more stable as a consequence of that.
Okay.
So who's going to be occurring in a polar protic solvent?
An SN1.
Why would the SN1 be occurring in the polar protic solvent?
Because it would want to have the protic, the hydrogen bonds to make the carbocation more stable.
Okay. Who's going to be occurring in a polar aprotic solvent?
SN2.
Why would the SN2 be occurring in a
Because
polar
it doesn't want
aprotic?
the hydrogen bonds to like cloud it to make it harder for the leaving group
Perfect.
to leave.
That's right. So if we have no hydrogen bonding, we can form what is called a naked ion, which is actually better for the reaction.
Okay.
Now we're going to get into the E1.
Okay.
Well, maybe before we do that, we could take just a couple example problems of sorry.
Like test problems, you mean?
Not test problems, just show you a couple examples of an SN1 reaction. So in this case here we have this alkyl halide, right? And in fact, let's just put it here. Right. So we have this alkyl halide. And what kind of alkyl halide is this? Is this a primary alkyl halide?
No, it's a tertiary.
Okay. And then we have H2O.
That's your nucleophile.
Right. The first thing that's going to happen in SN1 reaction is what?
Your leaving group is going to have to leave.
Sorry?
Your leaving group is going to have to leave.
That's right. So once my leaving group leaves, I will generate a carbocation. Then my nucleophile H2O would come in. Then I'll generate this here, but it will have a positive charge on it. That's right. And then we're done. Cool. Alright. Okay, now we'll look at we'll now transition over to the E1 and E2. So we're now dealing with elimination reactions. When we were dealing with the substitution reactions, we said that it was one group comes in and substitutes for another group, and that we were starting with an alkyl halide. In the case of the elimination reaction, we're also going to start off with an alkyl halide. Right? The only difference here is we're not substituting anything. We're actually kicking off one group.
Okay.
Once we kick off that one group, we will have to form a double bond as a result of it. So we're going to start off with an alkyl halide. We're going to have a base present, and we're going to generate an alkene. Right? So another way to kind of visualize this just trying to get you to visualize this a little bit. So this picture here, we have a boy in a chair, right? And this is his mom. Okay. So if the mom screams at the boy, then the boy will leave, right? And then we would just have the chair. Notice that we're something left, right?
Yeah.
But nothing else came back to replace what left. When we're doing an elimination reaction, something will leave and nothing is going to replace it.
Okay.
Right? When we do an elimination reaction, something will leave and nothing will replace it. Now notice that the thing that leaves is actually leaving because something is causing it to leave. So it is because the mom, perhaps, let's say that the mom is like screaming and yelling. Or let's say his name is Bob. Right? And the mom screams, "Hey Bob, can you get out of here," or whatever. And so he listens and then goes and leaves. So because of the influence of the mom, the boy left the chair. Now we just have a chair. Notice that the boy with the chair is different from just having a chair. So we are left with a different product than what we started off with. So we start off with an alkyl halide, and under the influence of a base, right? We would remove a proton and then kick off this halogen, generate an alkene. Cool.
Yes.
So in elimination reactions, something leaves. Actually, let's see, leaving group leaves. Leaving group leaves. And we generate a double bond. Right? So in an elimination reaction, something leaves and we will generate a double bond. Right? Now there are two kinds of elimination reactions. In both kinds of elimination reactions, we're using base. We're going to start off with a reactant. Right now we're focusing on alkyl halides. And once we react that with base, the leaving group will leave and it will generate a double bond, an alkene. Alright, so then the two kinds of eliminations is E2 and E1. Can you guess what E2 stands for?
Elimination bimolecular.
That's right. And what about E1?
Elimination monomolecular.
Perfect. So this is going to be okay. Now since this is elimination bimolecular, right? The rate determining step should be determined by what? What should the rate determining step be determined by?
Like how quickly the leaving group can leave? Or no, if it's bimolecular,
That's right.
it's determined by like how substituted whatever the carbon it's attached to is.
Okay, that's part of it. So this one is the E1 is elimination unimolecular. Okay. Remember, the reason why we're saying is bi is because of the kinetics, right? In the SN2 reaction, the transition state was determined, or the rate of the reaction is dependent on both the substrate and the nucleophile. Right? So in an SN2 reaction, the rate of the reaction was dependent on the substrate and the nucleophile. And because the rate of the reaction was dependent on those two species, we said it was an SN2 reaction. A substitution nucleophilic bimolecular. Because it follows second order kinetics. Because the rate is dependent upon two species. The same concept is in E2. The rate of the E2 reaction is going to be dependent on the base and the substrate. Right? That's why we're calling it E2 reaction.
Okay.
So bimolecular because it exhibits second order kinetics. Alright?
Okay.
And why do you think we're calling this one E1?
Why?
Yeah.
Because it exhibits first order cation.
Okay. So the rate of the E2 is going to be dependent on the substrate and on the base. Right? So it's dependent on this one and this one. So it's two things, right? That's why it's bimolecular. The rate of the E1 reaction will be dependent on what?
Just the substrate, maybe?
That's right. Just the substrate. Just like in SN1.
Okay.
So what we see here is that there's a relationship, right? There's a relationship occurring here between the 2's, right? The 1 and both SN1, SN1, SN2, E1, E2. There's a relationship.
Yeah.
So now, in particular, is this a new material here?
Yeah, sorry. Do you want the new material?
No, the old materials.
This is the old material. This is E1.
So now we're going to focus in on the E2 reaction. Alright, and in the E2 reaction, we're going to start off with an alkyl halide. Right, in this particular case that we're going to be looking at. Alkyl halide, we're going to react it with a base. We're going to generate alkene. Right? Now, the mechanism of the E2 reaction is going to be concerted. Right? And we said that concerted meant everything happened at the same time. So now it turns out that this is a little bit different, because in the SN2 we didn't want a sterically hindered substrate. But it turns out that the E2 does not care about the substrate. Right? So it doesn't really matter what kind of substrate you have, whether it's primary, secondary, tertiary, whatever kind of substrate you have. Doesn't really matter too much for the E2 reaction.
Okay.
One second. Alright, so it doesn't care about the substrate. So that means that for the most part you're going to see it on primary, secondary, tertiary. And most part you're not going to see it in a methyl, but it doesn't, again, it doesn't really care about substrate. But you're not going to see the reaction occurring all that much in methyl. So it doesn't really show a particular preference, but there is some competition, so some of these might be more just because there's a competition between SN2. But we'll get into that later on. So now we'll just take an example of this. Alright, so in this case here, we have this alkyl halide, and we're going to react it with sodium methoxide. Right. And we can just say that we are in some aprotic solvent. And now what's going to happen here, right? What's going to happen is that we're going to have hydrogens, right? Because remember, we're going to be using a base, right? So we're going to have an alkyl halide, we're going to have a base, and we're going to form an alkene, right?
Mm-hmm.
So it turns out that in order to remove this leaving group, I need to do a deprotonation first before I can remove this leaving group.
Okay.
In order to do a deprotonation, I'm gonna have hydrogens.
Okay.
And those hydrogens are gonna be here and here. So we'll get into this more.
Okay.